All right, so here we're going to find the derivative of y with respect to x of the equation of the tangent of x plus y is equal to x at the point 0, 0. So for this problem, we're going to need to apply a technique of implicit differentiation. And that's because we don't have y in terms of just x. We don't have what we say an explicit equation for y. We don't have like y equals where y is isolated by itself on one side and all the other terms with x are on the other side. So we use implicit differentiation, and that's going to involve using the chain rule quite frequently. So make sure you're very proficient with it. Here it is again, but of course, make sure you know all the differentiation rules, like the power rule, product rule, quotient rule. Okay, so let's get going. So with trig functions, I really emphasize particularly highlighting the input, because sometimes it can be a little abstract when you're like told to find the tangent of something, the cosine of something, the sine of something. So I like to always use parentheses more than most people, but again, that's just my style. But anyways, with implicit differentiation, we have, in this case, we want to always identify the functions. So the outermost function on the left is the tangent function. So the left side, you can write the tangent of, it looks like that pen is no good. I'm going to write the outermost function in black. So the tangent of, and inside of that, we have the x plus y function, x plus y is equal to x. So in this problem, we're going to apply the chain rule where we take the derivative of the tangent function and multiply it by the derivative of the inside function, which is x plus y. So differentiating the tangent function, we're going to have the secant squared function, the secant squared of x plus y. Leave the inside the same. And this whole thing, let me put that in double parentheses, is all multiplied by the derivative of x plus y. So all of that will be multiplied by the derivative of the inside. So the derivative of x, so doing one at a time, the derivative of x is just 1, plus the derivative of y, which is also just 1. But when we're differentiating a y term, we're going to also need to multiply the derivative by dy dx. So we'll have 1 times dy dx, or 1 dy dx. So all of that will be inside this red group, which is all being multiplied by this black group. And that'll be equal to the derivative of x, which is just 1. All right, now essentially we're just solving for dy dx now. It's really just like an algebra problem. So when you're solving for dy dx in what's called a differential equation, treat it like it's a variable for the most part. Treat it like it's a term. So you can multiply by it, divide by it, subtract, add it. So it's like 1 plus t. Let's say it was 1 plus t. Like let's say that was just, let's just think of this as 1 plus t. All in that red group. You're gonna divide by this, and then you subtract the 1 from both sides. So let's see what that looks like. So going over here, if we divide both sides by the secant squared of x plus y, this whole thing fades away. And on the left, we'll just have 1 plus dy dx. That'll be equal to 1 all over the secant squared of x plus y. Now, from here, we just subtract the 1, because this entire group is not really being multiplied by anything. So we subtract 1 from each side. And then so we'll have dy over dx is equal to 1 over secant squared of x plus y minus 1. So jumping to the next step here, we're going to get dy dx is equal to 1 over the secant squared of x plus y minus 1. Let me put that minus 1 in red, actually. And again, this is just more of an algebra problem. So we're going to write this 1 in terms of secant squared of x plus y, so we can combine like terms. So in other words, we just have dy over dx is equal to 1 over the secant squared of x plus y. And this 1 is just, you know, the same as secant squared of x plus y over the secant squared of x plus y. So then all we really have on the right side is 1 minus secant squared of x plus y over the secant squared of x plus y. Then dy dx is equal to 1 minus the secant squared of x plus y all over the secant squared of x plus y. So this is the equation of your derivatives. But we're not done yet. So be careful about this, because this is a common mistake with my students. I always have a couple where they'll work through a problem like this, they'll get the derivative right, and then they'll stop. And they'll lose, sight of what they're trying to find at the end. So they do all this right. So, the dy over dx is, great. So they know their calculus, but they just forget to evaluate it at 0, 0. So then they don't get full credit. They have to take off a couple points, and it sucks because they probably could have evaluated if they just went back to what they were solving in the beginning. So don't make that simple mistake. So all we're doing is evaluating this equation when x is 0 and when y is 0. So let's go back over here actually. So let me write it over here. So when x is 0 and y is 0, what we have is the dy dx. We're taking is going to be equal to 1 minus the secant squared of 0 plus 0, or the secant squared of 0, over the secant squared of 0. And then we evaluate this. Now, in case you need a little trig refresher, here you go. Let's remember what the secant, of a function, secant of x is equal to 1 over the cosine of x. And so if you want to evaluate secant of 0, that would just be 1 over the cosine of 0. And the cosine is, let me make that a little cleaner. The cosine of 0, as you should know, is just 1. So then this is just equal to 1. So it's just 1 over 1. So it's just 1. So what we have here is, what we have on top is 1 minus the secant squared of 0, or just 1. So 1 minus 1 all over the secant squared of 0. So all over 1. And so we just have 0 over 1, or just 0. So this is our final answer right here. Put that in red. The final answer is that the slope, remember dy over dx is just a slope of the function at a specific point. The slope of this equation at the point 0, 0 is equal to 0. There you go.